This is a problem about a landscaped artist who's enclosing a rectangular garden. So she's enclosing a 3,000 square foot rectangular region in a botanical garden. She'll use shrubs costing $45 per foot along 3 sides and fencing costing $20 per foot along the 4th side. Find the minimum total cost. So what kind of problem is this? This is an optimization problem. I'm trying to find the minimum it's going to cost. Find the lowest global output or input. Let's see. Find the input that creates the lowest output of cost. I said it right. Find the input that causes the lowest output in cost. So since I do have a physical shape here, I am going to draw a picture of it. So it's just 4-sided object, rectangular. I'm going to call these 2 guys X and these 2 guys Y for no reason other than I just want to. This cost me $45 per X. This costs me $45 per Y. This side costs me $45 per X because it says 3 sides here. And then the other side is just $20. Now the bit of information that I haven't even written down here yet is that I want 3,000 square feet. That's all the space that I have. So I know square foot implies area. So my area has to be 3,000, but also the area, besides being written as A, I can write it as X times Y, because the area of a rectangle is X times Y. Now I would like to come up with the cost of this job. So my cost is going to be the product of each of the variables with the particular dollar amount, all added up. So 45X plus 45Y plus 45X plus 20Y. If I simplify that, I have 90X plus 65Y. And that's my cost. However, it's a function of 2 variables here, X and Y. And we don't want that. We want a function of 1 variable because, you know, we don't know how to do things with multivariable yet. That's calculus 3. However, this area here gives me a constraint to work with. I can solve for Y by dividing both sides by X. So Y is 3,000 divided by X. That means X can't be 0 if I do something like that. So now I'm going to substitute this guy back into this equation to come up with a function and variable of just X alone. So 90X plus 65 times 3,000 divided by X. There we go. So in order to optimize a function, I have to find critical points. And to find critical points, we always have to have the derivative. Find critical points, find the derivative of the function we're trying to optimize. Before, though, I do that, I'm going to rewrite this with a power function instead of a ratio, because it's just easier to take the derivative of. So C prime of X, then, using the sum and difference rule, the derivative of 90X is just 90. The derivative of this guy, well, the constant multiplier rule says that I can write this down first. Then I take the derivative of this guy. Minus 1x, minus 1 minus 1 is minus 2. Doing a little simplifying, 90 minus 65 times 300 divided by x squared. That's C prime. This is a pretty long problem, so I'm just going to scoot down here a little more. Now the next step I have to do is find where C prime equals 0. Because that's where maximums and minimums occur, where the derivative of original function is flat. Or the tangent line to the derivative is flat. Derivative is 0. It's always been that way, it won't change. So I have to solve the equation 0 equals 90 minus 65 times 3,000 over x squared. Now, since I have this ratio, and this is a simple number here, I'm just going to add 65 times 3,000 to both sides. Oh, well, over x squared. And then I have this lovely setup here. Now what that allows me to do now is multiply both sides by x squared. And I have 65 times 3,000 equals 90x squared. Divide both sides by 90. I get 65 times 3,000 divided by 90. Taking the square root. Well, let me simplify this first. I go to my calculator and I type the buttons in, and it simplifies to 6,500 over 3. So if I just want to take the square root of both sides to get x, I get the square root of 6,500 over 3. Now, technically that is plus or minus, but I'm going to choose the positive one. Why? Because x is a distance. Now what I'm going to do is determine if this is a global min or not. Prove it. Okay, it could be a global max. I could have my cost function way off, so I have to figure out for sure if that's a global min. So what I did is I took my cost function right here and I graphed it to take a look at what it looks like. So my graph comes down and looks something like this. Now I know this function here, if x equals 0, it's undefined. That's why there's an asymptote here. And since this is a rational function too, and I write it with the common denominator of x and add these together, I realize that because the numerator has a degree larger than the denominator, that as x goes towards infinity, I have an oblique asymptote, so that means c of x goes to infinity. And same thing the graph shows, as x goes to 0, c of x goes to infinity, which makes sense actually, according to the information that I have. So since the square root of 6,500 over 3 is the only critical point, and both ends of the function c of x go up towards infinity, that forces, that's infinity, not just a scribble, but that's infinity, it forces x equals the square root of 6,500 over x to be the place, over 3, to be the place where minimal cost happens. The dimensions, it doesn't ask for the dimensions, but I know one of the dimensions, the x value dimension up here in the picture, the x value dimension here is the square root of 6,500 over 3. So let's figure out what the cost is, because really what they care about is what the minimum cost is. They don't really worry about the dimensions. Right now the question is asking for a minimum cost. So that means I have to evaluate c at the x value where the critical point is. C, not c prime. So it's going to be 90 times the square root of 6,500 over 3 plus 65 times 3,000 divided by the square root of 6,500 over 3. And after putting that in my calculator, I get the lovely number of 8,378.54. So minimum cost of the project is $8,378.54. If you want to find the dimensions, you know that x dimension is the square root of 6,500 over 3, and the y dimension is 3,000 divided by that, if you want to go that far. The question doesn't ask to go that far, but you could if you'd like. Say if you were the designer.